My name's Omar Sow. This is my poster for the default final project for CS224N. So the problem for the default final project is question answering, which we defined as given a context C and a query Q, how do we answer that query with a span of text CI through CJ from the context itself? That is, the output of this model is really a pair of indices into that context. And the span is the text of the context between those indices. So initially, I did just a quick look over of the data, seeing what kind of characteristics might be useful. Found that I could really limit question length and context length based off some results here from a quick histogram, seeing that questions didn't really tend to be longer than 15-20 words. Context also didn't tend to be longer than about 150-200 words. I also did some analysis of the length of the questions, length of the words in the questions, and length of the words in the context, and this feeds into an addition I made to the baseline. So speaking of baseline, we were provided with one, which was a GRU, and it had an embedding, attention, and output layer. Since I was a one-person team, I wanted to explore all three layers a little bit and try and make an improvement to each. So I'll walk through each of those. So first there was the embedding layer, and so the baseline at this point generated word embeddings for all the words in the query, all the words in the context. It's used glove pre-trained word embeddings. So to enrich this, to better handle out of vocabulary words, as well as to learn what it could about the structure of words and anything about words beyond that outermost layer of the full word. I added character level embeddings. So this worked by taking character IDs from the text, right? So that's just like the ID of each character within a list of like alphabetical letters and a few special characters. Get trainable embeddings for each of those IDs. So that was a whole new variable within the graph. And then passing these embeddings into a convolutional neural network with settings for like a window size, so it would pass through these characters, right, and be convoluted over a particular window of characters, and pass that over, so it would be regardless of word length, for example, right? Taking the hidden states from that convolutional neural network provided me with the final character level embeddings, which I would concatenate with the word embeddings already there to provide sort of an enriched embedding for the word itself, so it contained information about the word as a whole and then about each character within the word as they plate together, right? And that gets fed into the attention layer, where I added redesigned it to be a co-attention layer. And so this meant that it took the embeddings from before for the question for the context. It first applies a nonlinearity with trainable parameters to those question hidden states, question embeddings, and then uses an affinity matrix to generate attention distributions from question to context and as well from context to question, right? And I'll show you an example of that in just a sec. And then combining those, we get some of our final attention output, which feeds into the way that the model at the output layer makes its final decision about where it believes the correct answer span is. And so this was my smallest modification to the output layer of the baseline, which was that it previously had just been taking the probability distribution over the entire context and finding the highest probability start and the highest probability end and returning those. I modified it to optimize for the highest combined probability of start at index I times probability of start at index j, right? So it was looking to maximize that product probability, and it also was restricted to only consider cases where j came after I, which is to say the span ended at or after it started, which is logical, but doesn't necessarily happen in the case where j and I are picked independently to just maximize probability on their own distributions. And so that was something we were seeing in the baseline and we knew about. But given these modifications, I went from my baseline score and steadily improved. These are unofficial eval dev scores, right? So that's within the training. And I wanted to make these modifications, and as I was doing it, test them out over relative to the final amount of iterations, a relatively small number of iterations, to see that actually I was implementing it correctly, that there weren't some bugs, and there were bugs, and they were debugged. But this was done as an unofficial dev score to get me started, and I knew from the beginning I was probably going to focus more on tuning my hyperparameters. But even here we see that the baseline, right, my baseline had, this is all after 15,000 iterations, had performance of 0.43, 0.034, F1 to EM, and then co-attention got it a little boost on both fronts, and then character level encoding got it another boost, and then smart spanning gave it a final boost. At this stage, I wanted to do some analysis of sort of where it stood. So first off, I mentioned the attention distributions, and so I wanted to visualize those at this stage, look at the examples, see what was going on. So this is an example. Up here we see the question, and down here the context. So we have what word did the NFL commissioner use to describe the Super Bowl 50, what this Super Bowl 50 was intended to be, and then the right answer is spectacular. And so in this case, we had a correct F1, a correct result. So we had an EM match and then a full F1 score, right? But we look at the attention distributions here. We have question to context, and we see that it does pay attention fairly well around here to spectacular, which is our answer. Pays attention to this part here, thinking about the NFL commissioner. But we look at the context of question, and we see that it's actually paying attention incorrectly to the second quotation. We see a little bit of that here too, which is not what we want to be seeing, correct? We're looking for one word that the commissioner used. Right, so we see that there's a little weakness in the model, and we also see this is all a little bit spread out. As far as scores, we notice here that the yellow and the orange are the train scores, and those both rise to solid levels to F1 near 0.9 and EM above 0.7. But we see that the dev scores rise a little bit at the beginning and then very quickly level out, which indicates overfitting. And so my initial desire was to quickly get to hyperparameters. And since I knew I had created a far stronger model than the baseline, I wanted to regularize it and make it more generalizable to see what it actually was capable of doing. So I spent most of my time looking at different ways to regularize, and so there was looking at L2 regularization. So this was the coefficient. So there were different choices of the coefficient for that, right? 0 being, of course, no regularization. Then there was controlling the dropout. And I went past these values to larger values and saw no improvement. So I focused on within this grid of combinations of different values, and then ran them for 15,000 iterations, and then found that there was definitely one standout here of 0.25 dropout, 0.0001 L2 regularization. So I took that model, I ran it for 40,000 iterations, then took a look at the at further unofficial dev results to make sure that I was looking at something productive before submitting it to the test board and seeing what it got there. And you can see just by comparing these attention distributions that it is definitely correcting for the mistake of the past version of the model. Right here, it's paying strong attention to the part of the context that's talking about the NFL commissioner and the word spectacular in both the context question to context and the context to question, and it barely pays any attention to the second quotation, which indicates that it is actually learning that this is the answer right here with a little more confidence. And potentially here we might have gotten a actually wrong answer if there was a slightly different number somewhere. But finally, that model trained for 40,000 iterations was submitted to the test board, getting an F1 of 72.9 and an exact match of 61.52. So we see that still the exact match is a harder metric, and this remains lower here with overall lower growth than the F1 did. Still overall significant improvement on the baseline, but it definitely leaves me wanting to spend more time exploring the parameters besides these hyperparameters, and I detailed them a little bit in the paper. I detailed them in the paper report as well. That's like the kernel size of the convolutional neural network, it's the depth of the model, its word length. A few of these other parameters I investigated found that I wasn't seeing strong results, at least not as strong as tweaking the hyperparameters. So I decided to focus my attention there. But still now, with that focus even, happy with these results. But leaves plenty of other parameters to play around with and try to improve.